find the index of refraction of oil by plotting sine theta against sine theta, sine 1 theta against sine 2 theta, and we did the same for glass, and we got very slightly different numbers. But when we're doing this kind of stuff, we want to make sure we can take full account of the uncertainty. So I would like to show you how to do that. And there's a couple ways to handle that. One thing we can do is we can take this trig identity, which is something you'll learn in pre-cal, or you will have learned in pre-cal. But it's when you take the sine of an angle plus another angle, you do this calculation. Sine of the first angle times cos of the second, plus or minus cos of the first times sine of the second, where in this case A is going to be our incident angle as an example, and then B will be the uncertainty and that angle. So to find the uncertainty in a measurement where sine theta is what we're trying to find, and the angle is like 32 plus or minus 1 degree, you'll have, so A would be 32, B would be 1 degree. You just plug everything in. And so you'd get sine of 32 degrees plus or minus 1 degree would be 0.5298, and the uncertainty would be this number here, 0.0148, which is roughly 2.7% of this number, 0.52. So the uncertainty is about 2.7% when our angle is relatively small, 32 degrees. If we go to a bigger angle, 75 degrees, sine is pretty close to 1 there. And so when you do this same calculation, you plug in sine 75, cos 75, put that all the way through. So sine of 75 plus or minus 1 degree gets you 0.9658 plus or minus this very small uncertainty. And so the uncertainty is about 0.5% when your angle is at 45 degrees, which makes sense because as you get to larger and larger angles, less than 90 degrees, sine gets closer and closer to 1, which means that 1 degree uncertainty is less important. So the other logical way we could handle this is to sort of do the other method that we have done in the past, which is take the maximum value minus the minimum value and divide by 2. So the way we would do that is take sine of the angle plus the uncertainty, that would be your maximum value, minus sine of the angle minus your uncertainty, that'd be your minimum value, and divide that by 2. So I think this makes sense. It's not a coincidence that both of these should give you the same answer, but when you plug this in for 32 plus or minus 1 degree, you get exactly the same answer that you had right up here. So we can reasonably conclude we're getting basically the same thing. You will notice that this number, 0.5298, is very slightly different than 0.5299, and that's because here we took sine of 32 and then we did this little operation to get the uncertainty. Here we did sine of 32 times cosine of 1 degree, but if you do cosine of 1 degree, you get 0.99998 or something like that. So within a rounding error, these are within, they're close enough that we can go that. They're within 1,000th of each other. And when we do the same thing with 75 degrees, we get the same uncertainty as before, and we get, again, roughly the same value for sine of 75 with a tiny little rounding error. So I think both of these methods, since they give us roughly the same answer, we can feel pretty comfortable using. So now that we've looked at how to handle the uncertainty in sine of an angle, I want to show you on some sample data I borrowed from a student in our class. So the first thing we're going to do is we can look here. We have two graphs, one for glass and the slope of which, when we plot sine theta 1 against sine theta 2, the slope ends up being the index of refraction, which is kind of what we're looking for. So one of the motivations behind doing this is you can see how close our ends are, and the thing we'll want to look at is can we safely say that these overlap? Are they different? And we need to look at the uncertainty to do that. So let's just use glass as an example. What I'm going to do is come up to the data browser, and in here I'm going to add to glass a new calculated column. And so we'll call this the uncertainty, or the delta is what they tend to use in IB, in sine, and we'll say theta 1, subscript 1. Get lazy, so we'll copy that. And the way to do that is come down here to the function, and you want a trig function, we want sine. We're going to use the more simple method where you just add 1 to the angle subtract 1 from the angle, and divide the whole thing by 2. So we're taking the maximum value for sine, the min value for sine, subtract them, and divide by 2. So we'll do sine of theta 1. And while we're still inside of the parentheses, we'll do add 1, because that's the uncertainty, 1 degree. And we'll subtract, go back down to function, sine, same angle, but now we'll do minus 1. And we need to do the whole thing divided by 2. I'll hit done. And you can see if you look on this graph, it didn't really show up, even though we do have an uncertainty column here. So what we need to do is we need to go into the sine theta 1 and tell it to consider that column for our uncertainty. So to do that, what you do is double click where it says sine theta 1, go to options, and say for error bar calculations, we want to use the column the uncertainty in sine theta 1. And when we do that, we should see error bars pop up. You can see them just barely. Now what we'll do so that they show up a little bit better is we'll go back into that same location. We'll say that we want tiny points. We'll make it a circle, and we can see the uncertainty a little bit better. And also you'll notice that the error bars scale with the value of sine theta. The smaller the value for sine theta, the bigger 1 degree is when we actually look at it. So let's do that again. Let's copy, let's copy some of that stuff so we don't have to do too much work. So copy, that will be for our new column. Go back to our data browser. So we'll just add the same thing, but now we want the uncertainty in sine theta 2. And you'll repeat that same exact process. I do want to walk you through the whole thing, so just bear with me while I set this up. Yeah, we'll just type it in, no big deal. Sine of, now we're going to do theta 2 plus 1. Repeat that same thing, but now we're going to subtract. And then divide that whole thing by 2. Okay, so we should also see that show up a new column right here. We will tell sine theta 2, we'd like to use that column as the uncertainty, which is delta sine theta 2. While we're at it, we'll change this to small circles. Orange is fine. And when we do all of that, we should see, get that out of here, we should see error bars in both the sine theta 1 direction, up and down, and the sine theta 2 direction, side to side. And since in general here, if we look, sine theta 2 values are smaller, oops, let me get that out of the way. Since these are generally smaller, the error bars are going to be generally larger, which kind of makes sense. And so what we need to do now is we're most of the way there, but now we need to add in our slopes, the maximum minimum slopes that we could get for this graph here. So let me show you how to do that. We're going to select the whole region here and go to curve fit. We want to do linear, so we'll tell it to try fit. Make sure you're on linear, and then we'll switch it over to manual before we hit OK. That's going to let us change the slope. So if you double click on this little window, you can enable the line drag, and then you can, we're going to go for the maximum slope here, and you can drag that down. Now the recommendation from the IB is to do that by eye. This is close enough, and I will double click and turn off that line drag for our next attempt. So now I need to find the other slope. So we'll do the same process. Linear, try fit, switch it over to manual, hit OK, and it showed up. That's going to be my minimum slope here. Let's turn on line drag. Let's do that. Let's go for minimum slope here. So it's not crazy important that you hit every single one of the error bars. Like this one, I'm going to go a little bit farther so I can account for this one because it's kind of out of our way just a little bit. I'll turn the line drag off. So there you have, this is my uncertainty, or I'm sorry, this is my best value, the average slope. That was the linear fit. Here's my manual fit. That's the biggest the slope could be given the error bars. And this is the smallest the slope could be given the error bars. So since I'm on the computer and don't have a calculator handy, you could figure this out. the answer you'd report would be, this would be n, and then you'd take the difference between these two numbers and divide by 2. That would be your uncertainty, and then you'd round, of course, to report your answer for n. And then you could compare that, you'd repeat that same process. You can compare that to the oil one. It's a little tedious, but you'd basically repeat the same process. My guess is you could copy those columns over and just change the things, the relevant things. The other main reason I wanted to show this to you was because anytime you linearize something and get a straight line as your answer, so here the straight line slope was our answer, 1.5 was our index of refraction. This is the best way to handle the uncertainty, especially when you have complicated things like taking the sine of an angle and finding its uncertainty. So there you have it.